Hello everyone and welcome to the second topic of the SS3 Physics first term curriculum. Now this second topic is about gravitational field, and to those of you who have been following our videos, you recall that we did discuss about the concept of force for the year 1 student, the SS1 student, and we did mention there being two types of force. We have the contact forces and then the non-contact forces. And when we talked about the non-contact forces, one of those forces we did talk about is gravitational force. So we're going to be looking at this in more light in this topic known as the gravitational field. It's one of those topics that I find interesting, mostly because of Sir Isaac Newton and the backstory behind the development of the Newton's law of universal gravitation. You know that famous story about how Sir Isaac Newton was able to develop a new concept by just observing the fall of an apple from a tree, right? That's one of the stories that I really enjoy in my study of physics, and it's something that has built a lot in me, and I hope that it will do the same with you. Okay, so under this topic, we're going to be looking at the concept of gravitational field. I will look at what a gravitational field is, we'll define it in details, and then we go to the Newton's law of universal gravitation. You should be able to state the law and apply it to solve problems, which is why the next step in the study is to solve problems involving the law of universal gravitation. It's one interesting part of this topic, as that simple equation that is gotten from the law of universal gravitation is helpful to even determine the position and even trajectory of objects in our space. I'm talking about planets, I'm talking about even galaxies in outer space. You can calculate their position, you can calculate their motion, their trajectory using that simple equation. We'll also look at the relationship between gravitational constant and acceleration due to gravity. Now you see these two these parameters are denoted with the letters G. So gravitational constant is denoted capital G, while acceleration due to gravity is denoted small letter g. So both of them having G and G and having the name gravitation in them, I will look at how do they relate and how can you get one when you have the other. And then after that, we look at what is known as gravitational potential. And then we go to Kepler's law and the solar system. At this point, we'll be looking at our solar system. I will look at the planets that we have in the solar system. And then we look at even their natural and artificial satellites. After that, we then look at escape velocity and its value, which is something that whenever you're going to send a rocket to space, you have to understand this concept very well. If you're sending a satellite that is something that you want to continue to orbit around the Earth, you have to ensure that it does not exceed the escape velocity. Because the moment you exceed the escape velocity, whatever vessel that is being projected is going to leave Earth's gravitational field. So we'll be able to calculate what that velocity is. That is the speed at which, when an object is projected, it will be able to escape from Earth's gravitational pull. That's why it is called the escape velocity. And then we end this topic by looking at even more questions or more problems on gravitational field, picking questions from WAEC exams, from JAMB exams, and other kinds of exams like that. So this is going to be a lengthy one. Please ensure that you're prepared for this. But we're going to make it as interesting as possible. You know how we do right here on our channel. We ensure that it's not dulling. We're going to explain every concept that you need to know, solve it, and also give you some tips that will help you remember most of the important parts of the topic. So please get all your materials ready, and please, if you're yet to be subscribed, kindly take a moment of your time, click the subscribe button, and don't forget to share the video so that you can help many more people like you who needs the kind of video that we make right here on our channel. So please share the video, encourage them to engage with the video by liking the video and also dropping us a comment. So now if you're ready, let's dive into the world of gravitational field. Whenever we are looking at gravitational field, we are looking at a particular type of force known as a non-contact force. And that force is, there are three non-contact forces. We have gravitational force, we have electrical force, and we have magnetic force. See, these three are non-contact force, meaning that they can impose motion on objects that they are not in contact with. For example, when it comes to that of gravitational force, you see that the Earth, despite being over 380,000 kilometers away from the moon, it exerts a force on the moon that keeps it in orbit around the Earth. The same thing applies to all the other planets that are in orbit around the sun. This is because the sun has a force hold on all these planets and their own artificial and natural satellites. All of them continue to orbit around the sun because of the existence of what is known as a gravitational force. And this is because they are all within the same field, that is, they are in a region or space where the effect of the sun's gravity can be felt. So this means we have to be able to define what a gravitational field is. So let's write down what a gravitational field is. Gravitational field is a region or space around an object where the gravitational force of the object can be felt or experienced. Now, here's the thing. Many times when we talk about gravitational field, we always think it exists only around supermassive objects such as the sun, the earth, and big planets like Jupiter, Saturn, and the likes. But you see, gravitational field is a concept that goes even beyond this kind of object. You could also find gravitational force existing even in a significantly smaller object. What we just see here is that whenever you have objects within a region of space, they exert what is known as gravitational force, that is a non-contact force on other objects around them. Okay, and whenever an object is within the region or space where the gravitational force of an object can be felt, then that object is said to be in the gravitational field of that particular object. Like, for example, objects within the gravitational field of Earth will be forced to revolve around the Earth or fall into Earth. Okay, while objects within the gravitational field of the sun will either be forced to revolve around the sun or fall into the sun as well. Outside of this, they are free from the gravitational force of the object itself, that is, whether it's the sun, the earth, or other planets within our solar system. And it also exists beyond our solar system when we talk about even other galaxies like Andromeda and even every other galaxy within the observable universe. They all exert some amount of force. And it's said that those that exert higher amount of force are bigger stars, and of course the black holes have the highest amount of gravitational pull to them. Okay, so when you look at these supermassive objects, they all have gravitational force, and this force can be felt within a specific region. Outside that region, you are free from the force of that object. So every time an object falls within that space where they have to experience the gravitational pull of the object, they are said to be within its gravitational field. So one more time, if you're asked to define what a gravitational field is, you say gravitational field is a region or space around an object where the gravitational force of the object can be felt or experienced. Good one. Before we state the Newton's law of universal gravitation, let us look at the facts that we have already established. We know that every object now has a gravitational field around them. And any object within their gravitational field experiences its gravitational force. Now, you see that gravitational force itself, we can define it as a force of attraction that an object exerts on every other object in the universe. So whenever you have an object in space, it exerts a gravitational force on every other object around it in the universe. Okay, and that force of attraction is something that Sir Isaac Newton was able to explain when he saw that there has to be a relationship between the masses of the object, the distance between them, and all of this should be able to give us the force of attraction between these objects. And this is what led to what we now know as the Newton's law of universal gravitation. Now, this law has an interesting backstory in that it happened at a time when in London there was an epidemic that led to the closures of schools and other public places. And Sir Isaac Newton, while at home, began to observe the way and manner in which things fell around. Now, the story told us that there was an apple which fell, and he observed that and then began to ask questions on questions, just as how science does things. When you observe something, you develop an hypothesis, you test it, and then that leads to the development of a theory, right? I believe you are very familiar with the scientific process. Okay, now we don't know if truly it was an apple or if it's a different fruit, but the story is one that is always lingering among scientific people. Okay, where they said that observation led to many questions, and then he began to ask many of these questions and develop formulas, test them, and was able to derive what we now know as the Newton's law of universal gravitation. Now, what does the Newton's law of universal gravitation state? It states that every particle exerts a gravitational force on all other particles in the universe, and that force of attraction is directly proportional to the product of their masses and inversely proportional to the distance between the objects. Let's write that down. The Newton's law of universal gravitation states that every particle exerts gravitational force on all other particles in the universe. The gravitational force is directly proportional to the product of the two masses and inversely proportional to the distance between the particles. Now, you see, this law explains how planets revolve around the sun, how satellites revolve around different planets. It's what keeps the universe in balance, because there is this force of attraction between all the massive objects that we have in space, and that force is called the gravitational force. And the magnitude and direction of this force is determined by the product of the individual masses and the distance separating the two masses. So every time you're solving for gravitational force, you'll be putting two objects in perspective. You're looking at the gravitational force between those two objects, and it is always equal to the product. It is always directly proportional, to the product of the two forces, and inversely proportional to the distance separating them. Now, from this law that we have stated now, the Newton's law of universal gravitation, let us show this mathematically. It states that the force is directly proportional to the product of the mass. So if there are two masses here, so let's call one m1 and the other m2. So that will be m1, m2. And the same force F is inversely proportional to the square of the distance. Now the distance here is denoted r, so we call this r squared. Now what this means is that we can combine these two statements by saying F is proportional to m1 m2 divided by r squared. Okay, please take note, this is r squared, not r2. R squared is square of the distance between the objects. Okay, and you know what happens whenever you take out the proportionality symbol and replace it with the equality sign? What that means is that you have to introduce a constant. Okay, so that means F now equals, the constant is denoted G. So we now have G, m1, m2, all divided by r squared. So what are all of these? F is the gravitational force. Okay, m1 is mass of object 1. m2 is the mass of object 2. r is distance between object 1 and 2. And then finally we have G. G is known as gravitational constant. And the gravitational constant is approximately 6.67 times 10 to the power of negative 11. And the unit is Newton meter squared per kilogram squared. So this is the approximate value of gravitational constant. So with this, we can then begin to solve our questions applying the Newton's law of universal gravitation. With this, we can find the distance between two objects in space, we can find the mass of any of the objects, and we can find the force of attraction between the objects. So you see why I said that this particular equation can be used to do a lot of calculations about the different planets we have in space. In fact, when it comes to how we got to know the amount of planets we have in our own solar system, there's this story where we learned that what we know today as planets comes from a word called planetes, that is wanderers. That is, in time past, we used to think that objects such as the sun, the moon, and all the other planets that we could see at that time were all planets. But now, since the time of Copernicus, we've been able to discover some other planets. We've seen Mercury, we've learned of Venus, we've learned that Earth itself is a planet, we've learned of Mars, we've learned of Jupiter, Saturn, and the likes. And calculations help to predict the position of other planets such as Neptune and even Uranus. Okay, so with calculations, they were able to determine this because it was observed that the other planets that we know were not moving along the paths that we expect them to do. And this could only be because there is another object that is exerting a force on them. And by applying this calculation, we're able to determine the location of such kind of object if it does exist. And by the use of the telescope, we were able to discover that they were actually those planets. All from the calculations, or from this same law that Sir Isaac Newton developed many years before that. So you see how interesting this particular law is. But don't forget, when you state the law, you say that it states that every particle exerts a gravitational force on all other particles in the universe, and the gravitational force is directly proportional to the product of the masses and inversely proportional to the distance between the particles. And we can state that mathematically as follows: F proportional to m1, m2, F inversely proportional to r squared, and then when you combine the two, you have F is proportional to m1, m2 divided by r squared, and you introduce the constant of proportionality known as gravitational constant, which is approximately 6.67 times 10 to the power of 11 Newton meter square per kilogram square. Now, before we go on to solve questions, it's important that I mention this, that this value is an approximate value, not an exact value. So depending on the question you are solving, you could be given something different from this. You could be given 6.7 times 10 to the power of 11. You could be given 6.6 times 10 to the power of 11. You could be given 6.66 times 10 to the power of 11. Anything that is close to this is also acceptable. And whenever a question gives you a particular value to use, you have to use that particular value. Otherwise, the acceptable value is anything close to 6.67 times 10 to the power of negative 11 Newton meter square per kilogram square. This question says, two spherical balls of mass 10 kilograms each are placed such that the centers of the balls are 10 centimeters apart. Now, what is the magnitude of the gravitational force between the two balls? Taking that gravitational constant is 6.67 times 10 to the power of negative 11 Newton meter square per kilogram square. Now, to solve this question, let us highlight what we have been given. We are given that G, gravitational constant, is 6.67 times 10 to the power of negative 11 Newton meter squared per kilogram squared. Okay? We are also given that the masses of the ball are 10 kilograms each. That is, M1 is 10 kilogram. M2 is also 10 kilograms. Okay? And we are also given that the distance between the balls are 10 centimeters. So R is 10 centimeters, which is actually 0.1 meter. Okay, now this is all that is required to find the force, the gravitational force between the two balls. And from the Newton's law of universal gravitation, F there equals G m1 m2 all divided by r squared. So let's apply it. F therefore becomes G, which is 6.67 times 10 to the power of negative 11. Okay, now this is going to be multiplied by m1, 10 kilograms, okay, multiplied by m2, which is another 10 kilograms, all divided by r, which is 0.1 in brackets all squared. Now what does this give us? This will mean we have 6.67 times 10 raised to the power minus 11 times 10 times 10 is 100, all divided by, now this is 0.01. Okay, so now that we have this, let's make this into standard form so that we can work with it with this other times 10 raised to the power of 11, and then we can also work with this 100 here. So that will mean we have F equals 6.67 times 10 to the power of negative 11 times, now this itself can be written as 1 times 10 to the power of 2. Okay, so now that we have this, all divided by, now this itself can now be written as 1 times 10 to the power of negative 2. So let's see what all of this will give us. So F therefore becomes, all of this divided by 1 will still remain 6.67. That is 6.67 times 1 divided by 1 is 6.67. Now we have times 10. Okay, this is minus 11. This is plus 2. Okay, when this goes up, it will be minus 2. So minus 2. Now what does this mean? We have F equals 6.67 times 10. Now minus 2 is plus 2. So this is minus 11 plus 4. Okay, so we have 6.67 times 10 to the power of, now this is going to give us minus 7, and it is measured in newtons. And that's the solution to this problem. This question asks that we determine the force of attraction between the sun of mass 1.99 times 10 raised to the power 30 kilograms and the earth of mass 5.98 times 10 raised to the power 24 kilograms. And we are to assume that the sun is 1.50 times 10 raised to the power 8 kilometers from the earth. Now please note that this is not in meters yet, so you still have to bring it to meters. So let's solve. From what we have here, we already have, okay, solution. Given that mass of sun is 1.99 times 10 raised to the power 30 kilograms. Mass of earth is 5.98 times 10 raised to the power 24 kilograms. Okay, R now is going to be 1.50 times 10 raised to the power, now this is kilo, that is 10 raised to the power 3. So 8 times 10 raised to the power 3. And this is what will bring it to meters. So we can now tidy this up and say 1.5 times 10 to the power of, now 8 plus 3 is going to give us 11. And this is in meters. Okay. One more thing is gravitational constant G. It's not given in this question. So we are going to take it to be 6.67 times 10 to the power of negative 11 Newton meter square per kilogram squared. Now let's put all of this in the equation. Don't forget, the equation is F equals G. M1 in this case will be mass of sun. M2 will be mass of earth, all divided by R squared. So let's put in all of the values. So this will now be 6.67 times 10 to the power of negative 11 times mass of sun 1.99 times 10 to the power of 30 multiplied by mass of earth 5.98 times 10 power of 24. Now all of this divided by R 1.5 times 10 to the power of 11 all squared. Now when you do this, what does that mean? It means F now becomes 6.67 times 1.99 times 5.98 divided by, now this one is 1.5 times 1.5 because it is squared. Okay, now all of this multiplied by, now let me deal with the positive side first. So this would give me 10 to the power of 30. So now we are going to add 24 to that. Now this is minus 11. Now when you deal with this part, this will give you 11 times 2, which is 22. Which when you apply the law of indices will subtract here. So this will be minus 22 as well. Okay, you can now use your calculator to tidy up all of this, and then you should get an answer that states that F equals 3.53 times 10 to the power of 22, and it is measured in newtons. And that's the solution to this question. In our study of gravitational field, now we have learned about what is known as the gravitational constant, and we denote that with uppercase G. However, in calculations in physics, there is another constant known as acceleration due to gravity, denoted the small letter g, that is lowercase g. Let us now establish a relationship between these two. Both of them are denoted g, one in uppercase, the other in lowercase. Let us find the relationship between them. And in order to do this, we're going to consider the gravitational force of attraction on an object at the surface of the earth. Now, according to Newton's law of universal gravitation, we know that the force of attraction on that object at the surface of the earth can be gotten from this equation, where the force of attraction equals, now we're going to multiply gravitational constant g by the product of the two masses that are in question here, the mass of the object and the mass of earth. So we're going to denote the mass of earth as m subscript e, and then the mass of the object, let's just leave that as m. Okay? Now, all of this will be divided by the square of the distance between the two objects, which is basically the radius of earth. So let's denote that r. So radius of earth, capital R, then this squared. Okay? So now that we have this as the force of attraction on the object at the surface of earth, let's not also forget that that object on the surface of the earth has a weight, and that weight also is equal to what we know as the force on the object. So, and the equation for weight is mass multiplied by gravitational acceleration, or acceleration due to gravity. So if this is our equation 1 and this is equation 2, we see that both of them equate to force F, right? So since both of them are equal to force F, we cannot equate 1 and 2. Equate 1 and 2. So what this means is that mg equals g, mass of earth, mass of object, all divided by r squared. So now that we have this, let us make acceleration due to gravity the subject of the equation. Now what that would mean is that acceleration due to gravity therefore becomes gravitational constant multiplied by mass of earth multiplied by mass of object, all divided by mass of object multiplied by radius of earth squared. Now this is the mass of the object, this is the mass of the object, they can cancel out. That means acceleration due to gravity equals gravitational constant multiplied by mass of earth divided by radius of earth squared. And this is the relationship between acceleration due to gravity and gravitational constant. Now, working with this relationship that we have established, let us now estimate the mass of Earth, given that the radius of Earth is approximately 6.38 times 10 to the power of 6 meters, and that gravitational constant is 6.67 times 10 to the power of negative 11 Newton meter square per kilogram square, and that gravitational acceleration at a point is approximately 9.8 meter per second squared. Now, to estimate the mass of Earth, here's what we do. We have established that G equals gravitational constant multiplied by the mass of Earth divided by radius of Earth squared. Now, what this implied is that the mass of Earth can then be given as G, which is gravitational acceleration, multiplied by radius of Earth squared, all divided by gravitational constant. So this is what we're going to apply. So let's apply it. Mass of Earth therefore becomes acceleration due to gravity 9.8 multiplied by radius of Earth squared. Now that is, we have 6.38 times 10 to the power of 6. Now all of this, we square that. Now all divided by gravitational constant 6.67 times 10 to the power of negative 11. Mass of Earth therefore becomes 9.8 multiplied by, now let's square this. We have 6.38. When you square that, that will give you 40.7044. Now multiplied by 10. Now this would give you power of 12. You just have to do 6 times 2. And that gives us 12 there. Now all divided by 6.67 times 10 to the power of negative 11. Now to solve this, all you need to do is say 9.8 times 40.7044 all divided by 6.67. Now all of this multiplied by, applying laws of indices, 10 to the power of 12. Now when this comes out, it becomes minus, then what we have here, which is minus 11. So let's see what we are going to have now. Mass of Earth therefore becomes, so we tidy this up. We have 9.8 multiplied by 40.7044. Now when you get the answer of that, you now divide it by 6.67. And that is going to give us 59.8. All of this times 10 to the power of, now 12 plus 11, because minus times minus will give us plus, right? So we have to do 12 plus 11, and that will give us 23. So we can then write this in proper standard form by saying this is approximately now 5.98 times 10 power of 24. Now since we move this decimal place one place forward, that's why we add 1 here. So it becomes 24. And don't forget that the unit is in kilogram. So this is the estimated mass of the Earth. Let us define what gravitational potential means. Let's consider an object, okay? And then the object is taken from whatever point it is to a certain height h. We say that a work is done on that object to move it from the point it was before to the new height h, and that work done is defined as the product of the mass, acceleration due to gravity, and the distance in which the object is lifted. Okay? Now, this particular work here is done against gravitational pull on the object. It means that that particular object has what we know as gravitational potential energy, which is equal to this value that we have here. So in order to denote what gravitational potential is, we say that whenever you have an object, especially when we are dealing with large objects, okay, and then the work that you do to move a certain object from a point at infinity to a new point, from that object, that massive object in space, is what we now know as gravitational potential. So let's define it. Gravitational potential is the work done in moving an object at infinity to a new point. So that is when you move an object from a different location, it has its own gravitational potential energy at that point, and then you take it to a new point. The amount of work you do to change the position of that object is what is known as gravitational potential. So for example, an object hanging from the surface of the earth requires a certain amount of work to pull it down. Okay, that work done is the gravitational potential, and it is denoted V, where V is given as Gm divided by R. Now let's tell what each of these parameters mean. V here is gravitational potential. M here is mass of object producing the gravitational field. Now, I have used this particular definition here because it doesn't only work when you are dealing with just Earth. Any supermassive object in space have its own gravitational field, and as a result, when you move an object to infinity to another point, by the influence of the gravitational field of that object, then you are also solving for gravitational potential. So whether it's Earth, whether it's other planets, whether it's a satellite, whether it is a black hole, if you are solving the gravitational potential for an object moved to a certain point under the influence of the gravitational field of that object, then the mass of that object producing the gravitational field is required. Why? R is the distance from the object. So that is when you take it to a new location. That new location, you calculate the distance from that point to the center of the object producing the gravitational field. So now that we know what each of these means, let us calculate the gravitational potential of Earth. To find the gravitational potential at a point on the Earth's surface, let's take that the mass of Earth is 5.98 times 10 to the power of 24 kilograms. And we already know that gravitational constant is 6.67 times 10 to the power of negative 11 Newton meter squared per kilogram squared. And the radius of Earth, let's take that to be 6.38 times 10 to the power of 6 in meters. Now let's find the gravitational potential at the surface of the Earth. Remember that the distance we have to take into account in our calculations is the distance from the surface of the Earth to the center of the Earth, which is why we are using the radius of the Earth here. Whenever the object is far from the surface of the Earth, we also have to add that distance to the radius before we then proceed with our calculation. But in this case, the radius of Earth is enough. So let's solve. The gravitational potential V will be given as G, then mass of Earth divided by the radius of Earth. So let's put in the values. G here is 6.67 multiplied by 10 to the power of negative 11. Now we multiply that by the mass of Earth, which is given as 5.98 times 10 to the power of 24. Now all of these will be divided by the radius of Earth, which is 6.38 times 10 to the power of 6. Now you can use your calculator to compute this. Simple way is multiply this first. 6.67 multiplied by 5.98. Now whatever you get, you divide it by 6.38, and that will give you 6.25 approximately. Now all of this multiplied by, now let's apply the law of indices to this part. I'll start with the positive one here. So 10 to the power of 24. Now when you multiply it by this, it means you have to subtract it. You have to say minus 11 now. We are adding the power actually. So plus minus 11 becomes minus 11. Okay? Now when you take this up, according to the law of indices, because we have division here, it becomes subtraction at the top here. So that is minus 6. So now what we have is V equals 6.25 times 10. Now when we do this, 11 minus 6 is going to give us minus 17. So all we need to do is now 24 minus 17, and that will give us 7. So this is 6.25 times 10 to the power of 7, and it is measured in joules per kilogram. That's the unit of gravitational potential. Now one more thing before we close on gravitational potential is that you need to note that from the equation, since we have that V equals Gm to the power of R, it means that it depends on R. The farther an object is from the object producing the gravitational field, the lesser the gravitational potential at that point. So that is when you take an object farther from Earth, you are reducing the gravitational potential on that object. Okay, and which is why most times when this is discussed, you always find it having the negative sign in the equation. The negative sign there is only to denote that the farther you are from R, the lesser the gravitational potential. I hope you got that now. So with this, you can do a lot of calculations from finding gravitational potential to radius of Earth, mass of Earth, and even gravitational constant. Now let us learn about our solar system and what is known as the Kepler's law of planetary motion. Now, many of you already know by now that our solar system has a supermassive star known as the Sun at the center of it. So when we have the Sun in the center of our solar system, now we can't draw the solar system on this simple board, so I'm just going to draw a spherical shape like this just to tell you that we have a Sun. Okay, so let's call this the Sun. Now the Sun itself is actually a hot gas that is burning at such a temperature that is sufficient to sustain nuclear fission. And when nuclear fission goes on, there's always a release of high energy. And this high energy leads to the Sun actually giving off light and heat energy. So that's why you see the Sun is very hot. It has a surface temperature that is as high as 6,000 degrees Celsius. That's just at the surface. At the core of the Sun is way hotter than that. Okay, now this Sun has what we know as its own gravitational pull because it has a gravitational field around it. And due to this gravitational field, there are other celestial bodies that are caught in this field and forced to revolve around the Sun. Among these, we have planets such as Mercury. Then immediately after that, we have a planet known as Venus. And then we have Earth. Okay, after Earth, we have a larger one than Earth known as Mars. Now, you see these first four planets are composed mainly of rocks and metal, with the exception of Earth, which has water as well. Okay, now these four planets are called terrestrial planets. Now, beyond them, we also have bigger planets known as the gas giants. Now, because of the space, I'll just list their names. We have planets such as Jupiter. Then we have Saturn. Then we have Uranus and Neptune. These four planets are called gas giants, with examples such as Jupiter and Saturn having hydrogen and helium. Okay, they are supermassive as compared to the four terrestrial planets, Mercury being the smallest of these four, and then we see that Earth and Venus have almost the same size, and then Mars is way bigger than all of these. But when you compare them to the size of Jupiter and Saturn, the biggest of the planets we have being Jupiter, then followed closely by Saturn. These are supermassive planets. But you should know that these are not all we have in our solar system. There's also a part known as the asteroid belt right here between Earth and Mars, which is composed of large rocks called asteroids. They are also caught under the influence of the Sun's gravitational field. And you see all of these, they revolve around the Sun. Okay? And one thing you should know is that the closer they are to the Sun, the faster their speed of rotation. In fact, all of their movements, the way they move around the Sun, is described by these laws here, known as the Kepler's law of planetary motion. And it goes on to explain how the planets, how the asteroids, and other objects in space revolve around the Sun by using three basic laws. These three basic laws explain the motion of all the objects in our solar system as follows. The first law states that the planets each travel along an ellipse with the sun at one focus. Now, what this means is that the 8 planets that revolve around the sun, all of them move along a path called an elliptical path. Okay, that is an egg-shaped path round the sun, where the sun is at the center. Now, please take note, this does not mean that the sun is stationary while these planets continue to move around it. The sun itself is also under gravitational influence of black hole at the center of our galaxy. Okay, so as a result, the sun is also moving along its own elliptical orbit around that black hole, but the sun is always at the center of the elliptical orbit of all the 8 planets that revolve around it. Now, this is also one of the reasons why Pluto was declassified as a planet, because it takes a different orbit entirely, and also its size is different as compared to all the other planets that we have. So this led to the declassification of Pluto as a planet in our own solar system. So instead, it is called a dwarf planet. Now, the law 2 states that the line joining the sun and the planet sweep out equal areas in equal time. That is, when you take a line from the center of the sun to the planets around the sun, they all sweep an equal area of space. The distance is equal at all times. And then in the law 3, we have that the square of the period of the revolution of the planets are proportional to the cube of their mean distances from the sun. In fact, to break this down, to make it simple, the farther a planet is from the sun, the more time it's going to take to complete one revolution. I mean, from the time that Pluto, for example, was discovered, it hasn't even completed one orbit around the sun. That's because of how far it is from the sun. Now, when you consider other planets, take Mercury for an example. It only takes 88 days to revolve around the sun, while Earth takes about 365 1/4 days to revolve around the sun. All of this is based on the distance, and you too can calculate how long it's going to take for a planet to revolve around the sun by using this equation. The period, being the time that it will take to revolve around the sun, is proportional to the cube of the distance of that planet from the sun. So when you know these values, you can also compute them. Of course, when you take the proportionality sign, it introduces a constant. So you can then use that to then find the value of the constant, since you know how long it takes Earth to revolve around the sun, and you know the distance of Earth from the sun. Put that into consideration and find the constant of proportionality. Drop your answer in the comment section. Now, when we have planets that revolve around the sun, these planets themselves also have other objects that revolve around them. They are called satellites. It's not limited to planets. We also have dwarf planets in our solar system. Some of them do have satellites that revolve around them as well. So, when we know that satellites are objects that move around planets, this gives rise to the different types of satellites that we have. Now, there are 2 types. We have what is known as the natural satellite, and we have what is known as the artificial satellite. The natural satellites are the ones that are naturally occurring, that revolve around the planets, while artificial satellites are man-made objects that are launched into space and then caught in the gravitational pull of the planet and then revolve around that planet. So let's start with natural satellites. Planets, we know that there are 8 planets in our solar system. We have Mercury, Venus, Earth, Mars. We have Jupiter, and then we have Saturn, Uranus, and Neptune. These are the 8 planets in our solar system. Now, of these 8 planets, Mercury and Venus have 0 natural satellites. Okay? Here we are discussing natural satellites. Mercury and Venus have 0 natural satellites. Earth has 1 natural satellite, and that's what we see in our night sky as the moon, right? Mars has 2 natural satellites. Okay, now I'll move on to Uranus and Neptune. Uranus has 27 natural satellites, while Neptune has 14 natural satellites. Now, as of now, Jupiter has 98 natural satellites that has been discovered. Okay, there are still ongoing research to find even more natural satellites that move around Jupiter and as well Saturn. Saturn has the highest amount of natural satellites discovered so far, with about 146 of them revolving around Saturn. Okay, but when it comes to artificial satellites, I describe them as man-made objects launched into space to revolve around the planet. So since Earth is the only planet with human life on it, so it means that Earth is the one that has the artificial satellites revolving around it. Okay, we have artificial satellites such as the International Space Station, It's an artificial satellite. We also have other artificial satellites such as the Sputnik. We also have the Nigeria Sat-1 and many other satellites that revolve around the Earth. Now, the purpose of these artificial satellites, are either for research purposes, Artificial satellites can also be sent for weather monitoring. And then we can also launch artificial satellites for the purpose of communication. Remember when we talked about things like satellite telephones, satellite TVs, and the likes? All of these are communication networks that requires satellites to be launched into our own space. Okay? Now, you see these artificial satellites, we launch them from Earth at a speed. Now, the speed here comes into question here, because when you want to launch an object from Earth, the speed matters. There's something known as escape velocity, which we'll discuss shortly. You see, this escape velocity is the value that the speed of an object must not exceed, otherwise it will leave Earth's gravitational influence. That is, it will no longer be pulled towards the Earth. So when these artificial satellites are to be launched into space, they are always launched at a speed that is not above the escape velocity. It just has to be close enough to it, but it must not reach the escape velocity. As a result of that, it will then be caught in Earth's gravitational pull and then be forced to fall freely under gravity. And because of this, it then begins to revolve round planet Earth. It is always stuck at that position, spinning with Earth as it revolves round the sun. So now that we understand the concept of natural and artificial satellites, let us now look at escape velocity in details and calculate the value of escape velocity. So before we go on to then calculate the value of escape velocity, let's define what escape velocity is. We say escape velocity is the minimum speed required for an object. Now, when I say an object here, I'm talking about a satellite or any other object you wish to launch out of Earth, launched from Earth to just escape or leave Earth's gravitational influence. Earth's gravitational field. So that is the minimum speed that you have to launch an object for it to be able to escape Earth's gravitational pull, so that it will be able to get out of Earth's influence of gravitational pull. At that particular velocity is what we know as the escape velocity, and it's something that can be calculated. Now please mind you, when you are launching a satellite with the intent that it should continue to move around the Earth, you make sure that the velocity at which it is launched is not up to the escape velocity. It also requires a high velocity though, but the velocity must not equal the escape velocity, because once you get to the escape velocity or beyond that, any object launch will leave Earth's gravitational influence. Now, to calculate the value of this escape velocity, let us start first by using the equation from Newton's law, or a universal law of gravitation. Now, remember that from that law we have that F equals G, M, mass of Earth, mass of the object, that is mass of the satellite now, all divided by what? R squared. Now this R here, let's make it uppercase R, so that it can be known as the radius of the Earth. You know the value of mass of Earth, you know the value of the radius of the Earth as well. Now, working with this, we can now get an equation for work done. Don't forget that work done equals force times distance, right? Now, this distance is the radius of the Earth. So if we are working with that, we will now say the work done will now be force, which is now G M divided by R squared multiplied by distance, which is R. So easily you see here that this R will take out one of these. So the work done now will now be G, mass of Earth, mass of satellite divided by radius of the Earth. And we know that work done can be equated with kinetic energy. And what is kinetic energy here? Half mass of the object and velocity of the object squared. This velocity here is what we use to get the escape velocity required. Okay, now we equate this with G, mass of Earth, mass of the object, all divided by R. Now when you look closely here, you see M cancels M here, right? And then you can make V squared the subject by saying V squared equals 2G ME divided by R, which implies that escape velocity V equals the square root of 2G ME all divided by R. And this is how you get the value of escape velocity. Now, this still looks a little bit complex. If you use these particular values of G, values of mass of Earth, values of the radius of the Earth, you get the escape velocity. But if this still looks a bit complex to you, there's another equation you can use, which comes from what we have here already. We can derive the value of mass of Earth from the equation. Remember, when we said relationship between gravitational acceleration and gravitational constant, we concluded that G equals G mass of Earth divided by R squared, right? So from this, what can we make of ME now? What this implies is that the mass of Earth now becomes what? R squared, GR squared, okay? And then divided by G. So you see this value here? Let's plug it into this equation and see what we end up with. We can now say V, which is escape velocity, equals square root of, we have 2 multiplied by G. Now multiplied by ME, which is mass of Earth, that will give us what? G R squared divided by G, and all of this divided by what? R. Let's see where this leads us. From here, G cancels G, right? So now we have square root of 2G R squared. Now all divided by R. Now this cancels one of these, leaving us with the square root of 2GR. Now you see this can also give you escape velocity, which is a more simpler equation to work with. Okay, so using this value now, let's go on now to now find the actual value of escape velocity. So now we already have that V equals square root of 2GR. So let's estimate value of escape velocity. Now that would mean that we apply V equals the square root of, now please take note, what we have here is 2 multiplied by, this G here is acceleration due to gravity. Now, I've mentioned in multiple of our videos that it is not an exact value. This is because the Earth itself is not a perfect sphere. So as a result, the value of G changes depending on your location on Earth. But the average value is 9.87 in meters per second squared. Okay? So when we then multiply this by the radius of the Earth, don't forget the Earth is not a perfect sphere. So when it comes to the radius of the Earth, it has an average value of approximately 6.3 times 10 to the power of 6 in meters. Now when you compute what you have here, you will end up with an average value of escape velocity to be to the tune of 11,200 meters per second. That's an average value. So that gives us escape velocity at 11.2 kilometer per second. So whenever you are launching a satellite out of the Earth's gravitational field, that is, you want it to escape Earth's gravitational pull, you have to make sure that the velocity is above 11.2 kilometers per second. But for the satellites that you want to continue to orbit around the Earth, you have to make sure that it is lower than this value, but not too low such that it falls back to the Earth. Alright, so these are the values that you see that the space scientists always put into consideration whenever they are launching. This is why you see that space scientists have specific locations where they launch their satellites from. This is because at those points they have an actual value for the gravitational pull of the Earth as well as the radius of the Earth, and all things come together to make their calculations work at those specific locations. Don't forget, escape velocity is 11.2 kilometers per second. Let's solve more problems on gravitational field. In this particular question, we are asked to calculate the force of attraction between two objects of mass 10 kilograms and 50 kilograms, which are 10 centimeters apart. And we're given that the gravitational constant is 6.67 times 10 to the power of negative 11 newtons meter square per kilogram square. Now, here are some tips for you when you are solving questions like this, especially in cases of, say, if it's a JAMB exam, that is the UTME exams. You always have to put into consideration that this value given here, if it is not stated in the question, you can use this particular value because it is the average value of the gravitational constant. Otherwise, it could be given as something different, say 6.6 or 6.68. Anything close to this is also acceptable. When a particular value is given, you are to stick to that value. It is only when you do not have a given value that you apply this average value. I believe that's clear. And then secondly, always bear in mind that every of the variable you are solving with should be in the proper SI unit. In this case here, we have the distance between the two objects, 10 kilogram and 50 kilogram, as 10 centimeters, which is not in the proper SI unit. So you have to convert this into meters. And in this case, 10 centimeters is 0.1 meter. Okay, so with all of this, you can successfully calculate the force of attraction between the objects by applying the Newton's law of universal gravitation. So here's the solution. According to Newton's law of universal gravitation, the force of attraction here is the product of gravitational constant, mass of object 1, mass of object 2, all divided by the square of their distance, so r squared. Okay, so applying that, F therefore becomes G, which is 6.67 multiplied by 10 to the power of negative 11. Now we multiply this by mass of object 1, which is 10 kilograms, multiplied by mass of object 2, 50 kilograms, all divided by the distance apart, which is 10 centimeters. Don't forget, which is now 0.1 meters. So put it as 0.1, and in brackets we square that. Okay, so when you are solving a question like this in the JAMB exams where calculators are not allowed, scientific calculators are not allowed, one way you can easily do this is to ensure that you solve bringing each value to a standard form. That way you won't have errors in your calculation. So to do that, we'll then say F here equals, what we have here is 6.67 times 10 to the power of negative 11 times, this is 500, right? 10 times 50, all divided by 0.1 squared will give you 0.01. Now these are what you are going to bring to standard form, as F now equals 6.67 times 10 power of negative 11, right? Multiplied by 5 times 10 squared. That is the value for 500 in standard form. Okay, all divided by, now bringing this to standard form, you have 1 times 10 power of negative 2. Okay, now 6.67 times 5 divided by 1 is, it will still give you the value of these two. So let's find the product of 6.67 and 5. So we'll do that up here. 6.67 multiplied by 5. 5 times 7, that gives us 35. So we put 5, carry the 3. 5 times 6, that will give us 30 plus 3, 33. So 3, carry the 3. Bring your decimal points down. 5 times 6 is 30 plus 3, and then we have 33. So our answer there is 33.35. And when you divide it by 1, it still remains the same, which is 33.35. Now multiplied by, now let's deal with these index numbers. Okay, so we have indices there. Applying the laws of indices, you will then have 10. This is minus 11 plus 2, right? Because you have to add the power in this case. Now, since this is division, we then subtract this. So minus 2 will give you plus 2. Okay? Now, this gives us that the force of attraction is 33.35 times 10. Now, this is minus 11 plus 4. And that will give you minus 7. So now we have this in Newton. You can then go on to bring it to a proper standard form, an approximate value, and say F is approximately 3.3 times 10 to the power of, now because you have moved the decimal point forward by 1 step, you add 1 to this and it becomes minus 6, and in newtons. And don't forget that 10 to the power of negative 6 is a multiplier known as micro. So we then say F is approximately 3.3 micronewtons. And that's the solution to this problem. Now let's try to solve this question. It says the average radius of Jupiter's orbit round the sun of mass 2 times 10 to the power of 30 kilograms is 7.8 times 10 to the power of 11 meters. So what we have here is the radius of the orbit, and what we have here is the mass of the sun. Okay, now if Jupiter has a mass of 1.9 times 10 to the power of 27 kilograms, find the gravitational force the sun exerts on Jupiter. Please don't confuse this. The mass of Jupiter and the mass of sun, they are nowhere close to each other. this is still multiplied by 1,000. It's 1,000 times bigger in mass compared to that of Jupiter. So let's apply the equation from Newton's law of universal gravitation to then find the force of gravitation between the Sun and Jupiter using all of this information. So F equals G, mass of Sun, mass of Jupiter, all divided by the distance squared. So let's apply what we have. G is given here as 6.67 times 10 power of negative 11. Now we multiply that by the mass of the Sun, which is 2 times 10 power of 30, multiplied by the mass of Jupiter, which is 1.9 times 10 power of 27. And then we divide all of this by the radius. Now the radius, which is the radius of the orbit itself, so we have that as 7.8 times 10 power of 11, and don't forget to square this. Okay, so we'll solve the numerator separately, the denominator, and then we complete everything in our final answer. Feel free to use your calculator at this point. So for the numerator, this is what we have. 6.67 multiplied by 10 to the power of negative 11, and then multiplied by 2 times 10 to the power of 30, and then we multiply that by 1.9 times 10 to the power of 27, and the numerator alone gives us 2.5 times 10 to the power of 47. All of this divided by, now at the denominator we have 7.8 times 10 to the power of 11, and then we square that, and we have 6.1 times 10 to the power of 23. These are approximate value to one decimal place, do not forget. Okay, and then working with this, what do we have as our final answer? So we're going to do 2.5 times 10 to the power of 47, and then we divide it by what we have at the denominator, which is 6.1 times 10 to the power of 23, and that will give us a final answer of 4.1 times 10 to the power of 23, and this is in newtons. And that's the solution to this question. This question says, for a satellite which is close to the Earth's surface, its radius of orbit may be assumed to be equal to the Earth's radius, where r is 6.4 times 10 to the power of 6 in meters. Now we have to estimate the speed of the satellite and the period of rotation of the satellite. So in order to solve this, okay, here's what we have to apply. We are going to equate centripetal force to the force of gravitational attraction. And that implies that centripetal force mv squared over r now equals g, mass of Earth, mass of object divided by r squared. Now from here, m cancel m, r take out one of these, so it means v squared equals g, m of e divided by r, which implies that v becomes the square root of g, mass of Earth divided by r. So now we can find the velocity of the object. So let's solve. V becomes square root of 6.67 times 10 to the power of negative 11, which is the average value of gravitational constant, and mass of Earth has a value of 5.98 times 10 to the power of 24. Okay, and then we're going to divide all of this by the radius of Earth, which according to this question is 6.4 times 10 to the power of 6. Now use your calculator to compute all of this, and it will give you V, which is approximately 7,900. Okay, and this is in meters per second. You can also write this as 7.9 times 10 to the power of 3 meters per second, whichever way works for you. So that's the value of the velocity of the satellite. So we solved the A part. Now to solve the B part, we need to find the period of oscillation and the period of rotation of the satellite. Okay? And period of rotation T equals 2 pi over W. But W equals V over R. Okay? So when we put that into this, period of rotation therefore becomes 2 pi R over V. So let's compute this. This will be 2 multiplied by pi, let's take that as 3.142, multiplied by radius, which is 6.4, times 10 to the power of 6, all divided by the velocity, which is 7,900. Now, once again, apply your calculator to compute this. It will give you an approximate value of 5,000 seconds. Okay, so that will be the period of rotation of the satellite, which is approximately 83.3 minutes. And that's the solution to this question. Now, folks, you can practice with many more questions on gravitational field. Don't forget that the equations are not static. Sometimes you have to relate it with other things that you have learned, like as we did in this case where we related it with centripetal force. Do not forget your constants, okay? Some of those constants are not rigid. Like, for example, when it comes to the radius of the Earth, you have to know that the Earth is not a perfect sphere. So when the question gives you a particular value to apply, do that. But if not, you take the average value, which is 6.3 times 10 to the power of 6. Okay, and in this case, you see it is given as 6.4. Okay, so it all depends on how the question states it, and then the average value when they are not stated are the things that you take into consideration when doing your calculation. And don't forget that if you come across any of the calculation and then you like some help with them, we are always here to assist you in every way that we can. All you need to do is put the question in the comment section of any of our videos, and we'll definitely attend to all of your questions. And if you're yet to be subscribed to the channel, I would like you to take a moment of your time to click the subscribe button. And don't forget that you can also share our content with all of your friends who need the kind of videos that we make right here on our channel by clicking the share button, and always encourage them to engage with the videos by liking, by dropping comments, and also sharing it across their own platform. Thank you so much for being part of the video so far. This brings us to the end of our study on gravitational field. We continue to learn more every day, so keep it locked right here on Oya Learn. I'll be seeing you in the next video. Bye for now.